Can you confirm, Shani, that you can see the slides?
Yes, we can see the slides.
Cool. Well, thank you, Shani, for organizing the seminar. I'm really interested in the questions and discussions that'll happen. I'm also really interested to hear about Jack and his experiences coupling Fortran simulations to Python and ML backends, because I think that there's a lot of shared experience there. And this is one of the things I find really exciting about this area is that we are kind of charting some unknown territory about how to combine AI and numerical simulations together. And so there's a lot of room for creativity and a lot of room for different solutions and different ideas. And I just find it really great to talk about and find out what everyone else is doing and what everyone else's thoughts are. So just a little brief background to me. As Shani said, I'm a senior HPC and AI research scientist. I work with Hewlett Packard Enterprise. I lead a lot of our research collaborations that are looking at this question specifically about how to combine AI and numerical simulations. My background, though, is actually on the climate side. I worked at JFDL and I worked at the Canadian Center for Climate Modeling Analysis on both of their climate models, primarily focused on the ocean side of things, so both MOM6, and then I also still currently sit on the NEMO Developers Committee as co-chair of the Eddy Closure Working Group. So a lot of climate science is still near and dear to my heart, and I'm really glad that I still have the excuse to work with people in the domain to kind of figure out how we can use AI to advance climate science. So just as a brief primer, because I'm going to talk about some of our applications where we've used this tool that Shani mentioned called SmartSim.
Andrew?
Yes.
Just would you approach the microphone a little bit closer?
Sure.
I mean, just hope that it will be a little bit more clear to people.
Okay, let me see.
No,
let me just try. How's this? Is this any better?
Yeah, it's a bit better. Thanks.
Okay, cool. Okay, so yeah, so in this talk, I'm going to give a lot of examples about where we've used HPC and AI, combine those two things to actually advance some science techniques. We have a number of different ways that we've done this. So I want to just give a very brief overview about some common archetypes of machine learning that you may have heard about, and for the ones that we'll be discussing here. So in general, there's one very common one. I think the one that I'll talk about the most today is this concept of supervised learning. And so essentially this is saying you have some model that you want to train. So given known inputs and known outputs, derive some kind of relationship, right? So all of us who've taken basic stats have done similar things, right? So linear regression, just building a simple linear model falls under the headline of supervised learning, where you're just trying to constrain the two parameters of a line that best fits the data, right? So that's solely considered supervised learning. You could call it machine learning. There's so many different overlapping definitions, but fundamentally that's one of the big things, right? Is that you're just trying to derive some kind of relationship given known inputs and outputs. What distinguishes an artificial neural network, right, is from something like a linear regression, is that there's both linear and also nonlinear transformations, each of which have many, many free parameters. This is intended to mimic the way that we think that that brains work, right? Like that's one they call neural networks, where each neuron is responsible for kind of firing or not and transforming data in some way. The main challenge for an artificial neural network is that there's so many free parameters. As everyone's been paying attention to the news, there's projects up there going for hundreds of billions, up to 1 trillion parameter models. And of course, this means if you're still thinking about it in a statistical context, that you need a lot of data constraining those parameters, right? Like rule of thumb is you want an overdetermined system in order to actually get some that might be accurate and also generalized well, because otherwise it's like trying to fit a line with only one point, right? You have an infinite number of parameters that could fit that, and it doesn't make much sense to build a model off of that. I'm also going to talk about a paradigm called reinforcement learning. This is where you train a model to take actions within a given rule set based on a predefined reward function, right? So this is almost a way to get the computer to learn how to do something optimally. So the simplest example of these that people and most accessible are probably things like people have actually trained a machine learning network to just kind of randomly learn how to play a video game, right? There's predefined inputs that you can use to play that, to interact with the game, to interact with the physics of the game. And the goal might be just to like complete the level in the fastest time possible. So that's another paradigm of machine learning that I'm talking about today. And then third one that I probably won't talk about that much is unsupervised learning today. And that's basically finding relationships in unlabeled data. So something like a clustering algorithm would fall under that kind of category. But the important thing to realize is that for all these archetypes, they really rely on a lot of data to learn, generalize, and predict. And that's a fundamentally different way of approach to solving a problem than numerical simulation, right? In numerical simulations, we derive PDEs based on some kind of first principles, maybe some educated guesses, but largely speaking, we know what the terms are. And then the behavior of the overall system is an emergent phenomenon, right? So we can model the Navier-Stokes equations, apply boundary conditions, apply initial values, and then we get the emergent behavior of whatever the fluid system that we are thinking about. Whereas for most types of machine learning, those are not built in, right? Those are all just, those come from the data themselves. They're trying to learn what those relationships are. They're not core fundamentally implementing, for most classes of machine learning, they're not trying to implement physics into them. And so one of the big things that in our experience when we've been working with people is that we have been finding that there are some broader archetypes of where we can apply ML and AI. And they largely center around where the ML is actually integrated into the application. So I've kind of said there's 5-ish kind of paradigms that we're nominally thinking about here. But today I really want to talk about ML in the loop and ML around the loop. So ML in the loop is essentially embedding a machine learning algorithm of any variety at the time step level of the simulation. So these are types of things that I think that Jack's going to show today, that I'll show today as well. This could be doing inference, right? So you have a pre-trained model where you want to ingest that, you're feeding output from the simulation, make the machine learning model do a prediction, and then ingesting that directly in the solver, kind of at the time step level. You can also think about this in terms of training as well, right? Where you want to extract data from the simulation at the time step level, and then train a machine learning model. ML around the loop, this is where you apply an ML technique that uses the simulation, uses the inputs and outputs of the simulation to do something. So this could be just like automatic parameter tuning, right? If you wanted to say, I have 12 free parameters of the simulation, I want to try to get this goal, let's apply some kind of optimization technique to find the best version of parameter set that matches what our expectations are. ML around the loop can also be interpreted as like data assimilation. And I think there's some nascent work that is in the community as well, trying to apply ML techniques to replace things like 4D VAR or Kalman filters as well. So really briefly too, before we get into SmartSim specifically, I just wanted to talk a little bit about why I think about HPC and AI instead of this HPC versus AI. And I think that this is actually a dichotomy that numerical scientists and most machine learning engineers are actually on board with, that there is benefit to both of these paradigms. One where HPC or AI won't necessarily replace HPC in all aspects, but the combination of HPC and AI is actually the much more interesting one. So what I'm showing here on the right is predictions from ForecastNet, which is a transformer-like model that NVIDIA developed along with ECMWF to essentially do weather forecasting. So the plot on the top is the results of an inference from a machine learning algorithm, and the one at the bottom is from the standard ERA5 ECMWF, like intermediate forecast system, right? So as you can see, the patterns are largely the same. One of the interesting things about ForecastNet is because it is simply just a machine learning model, it's very quick to run. So it takes order seconds to actually do a forecast as opposed to do the full ERA5 integration. And so this might be for naive kind of outside users of HPC simulations, the question becomes, well, okay, if I can run this so much more quickly, so much more cheaply, why do I even need an HPC simulation? And so the big thing is that we don't know how to add process complexity a priori to machine learning models, right? Like there's no, we can define the layers of it, we can define kind of what the structure of the model is, but we don't know how to, let's say, embed moist physics into it a priori. And so you need something, more data from a simulation to actually constrain that and to teach a machine learning model how to do that. And then the other thing is, can they extract, machine learning models are very good at interpolating within the training data set. They have much more difficulty when they extrapolate beyond. So for things like climate questions, where by definition it's kind of out of scope from the data that it may have been trained on, it may not retain as much information, as much skill going forward. So that's a really kind of quick overview of this tension that exists, but I think that it's actually not that much of a tension. I think that they are both complementary kind of tools in very much the same way that numerical simulations never replaced theory and they never replaced observations. You know, it's just yet another toolkit that we can use for scientific advancement. But of course, because this is a kind of a new field, there are some challenges to combining HPC and AI. So some of them are numerical, right? So like, how can you characterize the stability and accuracy of an ML model in a numerical context, right? When you talk about accuracy of a machine learning model, you're not talking about the order of accuracy, you know, based on some Taylor series expansion of a discretization of a PDE, right? You're just talking about how well does this predict the data? And we don't know how that necessarily maps onto numerical techniques, you know, standard time integrators that we use in all areas of numerical science. So that's an open question. That's one that I've spent a lot of time thinking about, but I won't present today. Today, I'm really going to talk more about the technical challenges. And again, Jack will also have an answer to this as well. So first one, how do you connect Fortran C and C++ code bases to machine learning packages, right? Most of the time, people are interacting with these ML backends in a language like Python. They do often provide a C or C++ front end that you can access a lot of the functionality of that ML backend. But there's also a lot of challenge to that because Fortran does not necessarily natively talk with C. There's been advancements that allow this ISO-C binding, but there's still some plumbing that needs to be done there. And then the second question that my team thinks about a lot is, how do you appropriately balance GPU resources when you're really running a predominantly CPU-based code? So this is the case, right, where it's like NeMo is still pretty much run on CPU, MOM6 is run on CPU. So on our supercomputing systems, if you have nodes that have both CPUs and GPUs on every single node, you know, you're kind of wasting the GPU in a lot of those times. And especially even in the machine learning applications, which we'll demonstrate today, the GPU need is actually quite small in comparison to a lot of the capabilities of today's modern accelerators. So how do you actually take advantage and maximize utilization of those high value, high cost GPU resources in a supercomputer is also a challenge that my team has thought about quite a lot. So as Xiaonie mentioned, the team that I am part of is SmartSim. So SmartSim is this open source library that HP has developed that helps bridge the divide between the traditional numerical simulation and data science, right? So fundamentally, we take a loose coupling philosophy, which means that we don't embed the actual machine learning libraries inside of the application themselves, nor do we actually is the inference necessarily done on the same processes as the simulation is running. The way that we do this is by essentially farming out that task to what we call an orchestrator. So an orchestrator is a database that sits separately from the simulation. But unlike a normal database, which can only store data, the orchestrator that we actually use right now is called Redis, that we are transitioning to a new solution, hopefully within next year. But essentially, this database can also store AI models, and it can also run calculations themselves. So the way that this essentially then works to actually do an inference or store information is that your Fortran simulation uses what we call Smart Redis, which is just a very lightweight client library that you embed into your simulation. And that client sends and receives data and issues commands to this orchestrator that sits separately from the processes of the simulation. The other benefit to this is that the orchestrator can also be distributed across multiple nodes. So if you really do have large data intensive applications, you can distribute them across multiple GPUs, across multiple nodes themselves. So you can just expand or contract the orchestrator to meet your computational demands of your application. The last kind of advantage of this is that the orchestrator really becomes the hub of a spoken hub model for data and AI models. So you can imagine that you can connect basically an arbitrary number of these clients from any sorts of different applications, and they can all use the orchestrator as a mediator of data and to do interim calculations that you might need to do to transform from one application to another. So we can do things like attach machine learning model. We can attach a machine learning training script that can extract data from the database, run that asynchronously to the simulation. We can extract data from the simulation that's been stored in the database into a Jupyter notebook and visualize output from the simulation while it's running, and all sorts of interesting things where the simulation is just one component of an entire ecosystem that's producing data and consuming data. And so this opens up a lot of interesting new applications that people can build and can advance science. So just really briefly, creating a SmartSim experiment, there's essentially two steps. So one, you need to embed some smart runner calls into the application itself. So an example of that in MOM6 is here on the right. This is about as much code as you need to add to a Fortran code in order to do an inference loop. It's essentially creating a client, using the methods on that client, like put tensor, to actually put some data from the simulation into the database, calling this run model command to say, like, please do an inference on this model, using this model with this data, and then unpacking the tensor to actually retrieve the output from that inference. So it's a relatively small amount of code that needs to be put in the Fortran stuff. It's all native Fortran, nothing that should be crazy unfamiliar for Fortran users. We also provide similar interfaces in C and C++. And then the second step is you have to write a driver script that uses the SmartSim Python library to describe and launch your experiment or application. An example that's given down here, a lot of this is kind of boilerplate, but there is a little bit of a learning curve just to understand how to describe the experiment, how to launch the experiment. But we try to do a good job to make it both portable, so that if you went from a machine that was Slurm based to one that was PBS based, you could kind of go between those pretty easily. There's also a lot of other different features of SmartSim that might be useful in these contexts, including the ability to configure your simulation and the ability to launch ensembles of simulations, and also define a workflow itself. And we have many examples of these. I won't list them all, but if you're curious, we have a bunch of these integrations and examples where we've done SmartSim experiments with different types of use cases in all these domains in all these models that you see on the bottom left. So now I just want to kind of run through using AI in the loop. So this is the first project that we did with SmartSim, where we embedded a machine learning model into MOM6 to actually predict eddy kinetic energy, which is then transformed into both the Jet-McWilliams, the Reddy diffusivity, and then the eddy viscosity terms in the momentum equation. We know we're basing this off of the original scheme called MICI, where there was a prognostic energy EKE equation approach. And instead of integrating that EKE equation, we're using the machine learning model to predict what the subgrid scale kinetic energy should actually be. And this was mainly identified because we know that prognostic EKE model has actually some questionable approximations that may be first order. And so we thought that embedding this neural network that was trained on trained on a high resolution model would actually work better. So the way that this works, like I said, every single MPI rank of the simulation sends features from MOM6 to the database. It then calls this run model command in the database. That database then does it locally there, and then you retrieve the inference results in MOM6. So the only time that you actually have data being sent over the network is on the send and the retrieve. It's not really, there's no real data movement that's done when you actually run the machine learning model. And so we did this, we had 12 ensemble members, and so we ran this on basically 200 nodes of a quarter-degree realistic ocean model configuration of MOM6, and only used 16 nodes for the database itself, right? So for some other kind of solutions out there, where if you are directly embedding the machine learning library and want to use GPU acceleration, either you have to do some bookkeeping to figure out which nodes have GPUs on them, or you just have to require that every single node has a GPU on it. So both of those things are obviously achievable, but we think that this is a simpler approach that makes more sense to kind of like, have this offline or off node inference server essentially that can do these computations for you. Obviously, it's really important that we don't blow out the cost of the simulation when we embed AI. And so one of the things that we were very happy about was that we only decreased the performance by about 10% when we embedded the machine learning model. And that was largely due to the actual cost of running the simulation itself and not the communication overhead by doing this data transfer back and forth. We also did this, we had the opportunity to run on Frontier, which is the first exascale machine out at Oak Ridge. And so here we embedded a CNN that was published in literature 2 years ago into MOM6 at the Baroclinic time step, so 900 seconds. And this was, we had extra large allocations, so we wanted to stress test the architecture. And so we were able to scale the simulation to 672 nodes. Using 20,000 CPUs and up to 5,000 GPUs at once. The scale was not really needed. Let me just be very clear. Like, this was not intended to be anything that was, demonstrative of the scale needed or computational intensity needed, just to scale the system. And what you're seeing on the right here is that is the service relative vorticity from the CNN-based backscatter model that was embedded at the Baroclinic time step. So you see a lot of the feature of the ocean spinning up, right? You see the Gulf Stream, you see Gulf of Mexico eddies that are spawning off, you see, equatorial waves and all that kind of fun stuff. So at the very least, we know this model is doing no harm. And now I just want to transition really quickly into some AI around the loop applications. So one thing that has been really kind of interesting to see is that people do want to train neural network surrogates. And so there are a number of CFD problems that can be posed in this kind of context. So one challenge, though, is that in both the simulations I showed before, was that the models were trained offline, right? So they were not actually validated as part of the training in the coarser resolution context. So we don't actually know a priori that, so nothing about the training or the improved skill of that coarse resolution model goes into the training at all. And so this actually could be a problem because we don't know whether that ML model will ensure that the simulation is stable. We don't know if it actually improves the accuracy of the system. And so if you turn this, though, into a reinforcement learning problem, where the skill improvement of the course simulation is a fundamental part of the machine learning training, then you can actually get a much better model. So in this particular case, you train a model of turbulence in situ from a high resolution run. You use the agent will predict this Magorinsky coefficient, train this kind of like smaller model, and then the reward function is to basically compare the spectra that you get in your low resolution LES run to your DNS solution. I'll skip that for now. And so what the authors basically showed in this when they used SmartSim to build this kind of reinforcement learning application using their CFD code, they found that the RLL model took about a day. It took about a day to run on 8 nodes and 8 NVIDIA A100s. But when they trained this model in situ, the result was just essentially that it could actually make this LES simulation match the energy spectra of the DNS simulation. The actual cost of running that inference once it was trained was about 10% again. So not bad, especially in comparison to try and do something like implicit LES versus or DNS even. And then there's also flexibility. The other benefit of doing this, there's flexibility in defining what the reward function is. So if you care more about the kinetic energy spectra, you can define a reward function for that. If you care more about, momentum flux in and out of the system, you can do that. But you can basically apply any reward function you want. And then lastly, I think this is the last example I'll have. This is an example of where they, again, took reinforcement learning, and the goal was essentially to say, if you have the ability to inject momentum into the system, can you stabilize a turbulent wake, right? And can you teach a machine learning model to actually do that online based on what it sees? And so in this particular case, this is a classic, cylinder in a box, where they have the ability for the machine learning model to inject momentum at the top and the bottom of this cylinder, and then they want to try to teach another machine learning model to figure out when to inject that momentum. And so they ran this model, and then if you can see, the top one is the uncontrolled one, and the bottom one is the optimal RL policy, right? So in the bottom one, you have this long extension of a more stable core of the low pressure zone behind the wake of the cylinder. And that's just from this machine learning model kind of just injecting momentum at the top and bottom of the cylinder here. So in a very different context, but related kind of at extract layer, this is essentially what data assimilation does, right? We're trying to find what novelties and increments that you could actually do to improve and make the simulation match, observations with some known errors associated with it. So this is yet another example where we think that there's a lot of opportunity for the combination of HPC and AI to advance data assimilation techniques. I'll skip that just in the interest of time. I'll skip this as well if anyone is interested. I'll just briefly mention this. We work with a lot of groups and are always looking to work with more people to do interesting things. So there's a lot of things that we're working on, in particular with the OpenFOAM group, which is a CFD, open source CFD solver, doing things like online training and inference to do advanced interpolation. So as this grid moves into forms, if you want to snap it to a new grid while conserving whatever you want, you can create a neural network to do that fancy interpolation. We're also thinking about doing training at the time step level at scale with this MFIX-EXA application. So that's essentially saying, we know that our models can generate exabytes worth of data over the course of the entire life of the simulation, but we often only train on some small subset of it. So how can we actually use SmartSim to extract information and effectively train a machine learning model at the time step level? So I'll just close with some general takeaways from my team's joint experience in this. So that one, I've already talked about this a little bit. There is a fundamental tension between AI for simulation and general AI. There's a lot of news about really big AI models, but really practically speaking, a lot of us in the science domain, the problems are simpler because we know that there is a pattern to it. We can describe them with PDEs. And then also we need them to be small enough so that you can actually run the inference in a reasonable amount of time compared to the time step of the solver, right? You hear all the time that ChatGPT takes 5 seconds to run. It's 5 seconds added to every single time step of a simulation like NeMo of MOM6 is effectively blowing out the computation by a factor of 100 or 1,000, right? So that's just not practical. And so we need small, compact models that work well and understand physics even to a certain extent. Second big point is that we are seeing a new paradigm emerging for computational science, where it's not just the simulation that's the scientific output, it's the actual full workflow, right? The combination of many different components working all together to actually come up with a scientific result. And so AI might be a component of that, but also this is a challenge for existing workflow tools because a lot of them assume that it's a simple graph that you can kind of just flow through in some way. But for a lot of things that we're thinking about, they actually have loops and conditionals. You might want to run this simulation and depending on the output of this component, go to a different one. So we need to think about ways of making that easier to describe for scientists and figuring out then what other new science we can do once we have the ability to describe those complex workflows. And then lastly, I think this one is really key and near and dear to my heart. Collaboration between domain and computer science is key to advancing the science, right? It's such a complex world out there. AI is moving very quickly, HPC is moving very quickly, science is moving very quickly. So try to stay on top of your game requires 4 full-time jobs to do on your own. And so who wants to do that? well, why not just collaborate with other people? And there is really a benefit to just being challenged both within your domain and outside your domain to actually come up with creative science. Yeah, so I'll just kind of leave with this slide here. I won't necessarily talk about it too terribly much, but I hope that I've, in the 20 minutes that I've, 24 minutes I've given, that I've convinced you that there is benefit to doing HPC and AI. I probably am preaching to the choir a little bit here since you're already at this seminar. However, I hope that there's some interesting things and paradigms that my group has done that might be of interest to you. And if you are, please reach out to me. We collaborate with many different people, many different domains, and that's essentially my full-time job. So if you are interested at all, please reach out to me, and yeah, I'd be happy to have a chat with you about anything that you've seen here today and or any proposed research that you may have. There's a bunch of information about SmartSim itself. There's talks that we've given, some case studies, and also the repository itself with documentation. So if you're interested, you can go to the repository, star us, and keep apprised of any developments that we might have. And other than that, I'm happy to take questions. And also thanks to all of our collaborators who contributed material to this talk as well.
Thank you very much, Andrew, for this very complete presentation about SmartSim. And it's very interesting to see diverse applications of this tool in different models and different problems. So thank you again. So is there anyone who would like to ask question to Andrew? Yeah, yes, go ahead. Rodwan.
Hi everyone, and thanks Xiao, Andrew, for this really nice presentation. Actually, I was interested also in the parameter estimation part, but you skipped it. So can you say something about that part also? I was
Sure. Yeah.
It's okay.
So
yes.
This one here, right?
Yes, please. Yeah.
So this one is essentially we apply, Bayesian optimization is a nice black box optimization technique to kind of sort of do parameter tuning. One of the problems though with almost any kind of optimization technique that you use, right, is that the black box function that you're trying to optimize is often something like a climate model, right, which takes days, weeks to run. So how you improve the convergence of the optimization technique so that you don't so taking, for example, 10 optimization iterations if you think a climate simulation takes maybe a week to run 100 years or so, right? That's a very expensive optimization loop. So the question here is, can you actually use something like just the fundamental basis of Bayesian optimization to improve this? So instead of just doing one test of a parameter set at once, we essentially use SmartSim to launch ensembles of simulations with different parameter sets. And so we find that actually improves the time to solution because the Bayesian optimizer can explore a broader sense of the parameter space at each step, and then also basically improve that Bayesian representation of the function that you're trying to optimize there. So, we've done this study where essentially we take 50 Bayesian optimization steps, each one doing just one parameter set per iteration, or we do it where we do 5 parameter sets at once, but do 10 optimization loops, right? So the total number of calls to the simulation is the same, but you just scale out horizontally. And so it takes a fifth of the time to actually converge to a reasonable solution for that. So this is one of the things where we think that this is cast under the archetype of AI around the loop, because you're applying some kind of numerical technique, ML-like technique to solve a problem like that. So this is one of the interesting areas. We did it with a toy problem, so who knows how well it'll extend to many more parameters and a much more nonlinear system. But we do see a lot of interest from people in doing things like this with more complex simulation.
Yeah, right. This is interesting. Is this really tailored for the package from scikit-learn? Because I'm familiar with that package. If I would like, for example, to use another package from another library.
Yeah, no, it's not really. So the example is tailored to scikit-learn because basically it was there. But the only thing that you really have to do if you have a different optimizer that you want is just to have some way to query the, to get whatever parameter set that your optimizer is telling to explore, and then that gets fed into SmartSim. SmartSim configures the simulation and then goes through. So really, it's the outer wrapping of the simulation or of this example that you'd have to replace if you wanted to use something other than scikit-learn.
Ah, cool. Thanks again, Andrew.
Yeah.
Thanks.
Yeah, and there's a notebook here. Xiaomi is going to share the
Yes.
slides, but there's a notebook there if you want to just see the full write-up.
All right, noted. Thanks.
So, any other questions? Maybe I have a few questions, Andrew.
Sure.
Yeah. COO, in this lab and also in EPSL, we have a lot of climate models. And around these climate models, we have developed useful tools such as libEGCM and XUS. IGCM is a useful tool to manage the simulations in an automatic way. XUS is a tool useful to prepare input-output data for the simulation. I see that in your example, we could use the SmartSim and to run simulation in multi nodes and multi processes. I'm just wondering, is it doable to combine the SmartSim with the libEGCM so that the job management could be more automatic?
Yeah, so I think that this is where we're very cognizant of the fact that there are a lot of these so there's a lot of feature overlap with the ability of SmartSim to configure and launch simulations with a lot of the tooling that the climate modeling labs have already. So in those cases, we try to do basically just incorporate ourselves wherever the developers of the Climate Modeling Center want us to be incorporated at, right? We have the ability to launch all these things through SmartSim. You don't have to. I think the only thing that you really need to do is probably launch this database with SmartSim, because that might be a little challenging to describe as in the workflow managers that the Climate Modeling Centers have. But it's pretty easy to kind of extract the information you need once that database is spun up and embed it into the simulation that you need to. So yeah, so the short answer is yes, like we can combine these things. We're talking with NCAR right now to try to figure out how it fits into SEAM, which is their kind of experiments and model launching kind of thing. And so far it's been pretty easy for them to do so.
Okay, it's very interesting to know that. We could talk more about it later. Another question, since we talk about database, the transfer of data, and so SmartSim uses Smart Redis for the data transferring. Does it mean that when we embed a machine learning model into the climate model, if the data array that need to be transferred has quite large data size, then they may the performance of combining SmartSim with the climate model could be somehow affected by this.
Yeah, so that's a good question. And I think that, even if so I think that the answer is that we think of our simulations as being very large, but in practice, you know, like a large ocean model might be something like 1400 by 1000 by 100, right? So like that still represents hundreds of megabytes worth of data. You know, we're not talking necessarily about terabytes worth of data that are being generated every step of the simulation. So if you're given the speed of our interconnects, which are